Well, hello everybody. My name is Sebastian Saa. I'm the Associate Director of Agriculture Research at the Almond Board, and I would like to welcome you to our irrigation science session titled New Perspective in Irrigation Management. Tom DeBall, our Senior Manager in Outreach and Education, and I have put together what we think is an exciting agenda for you. You can see it there on the screen, where we will start with Professor Ken Shackel from UC Davis, who will share with us new insights about the evergreen question, when do we start irrigation early in the season? We will then move to present the latest results in tree evapotranspiration and novel ways to estimate how much to irrigate, thanks to the work done by Dr. Mcelrone and Dr. Melton from USDA and NASA, respectively. Finally, we will share with you the latest result from Dr. Kisaka, who has been implementing precision irrigation management in almond orchards, sponsored by a research project that he has with us. So that's it. Stay tuned, enjoy the next 40 minutes of presentations, and please feel free to send questions via email directly to the speakers. You can see their emails displayed there. And so we will display the same slide that you see now on the screen at the end of this session, where you can take note of the emails if you haven't done so already. But again, if you have questions after this 40 minutes of talks, feel free to email the researchers. That's it. Can you go next?
All right. Hi, I'm Ken Shackel. I'm going to be talking about irrigation management, in particular, when to start. And you can think about this as a Goldilocks question. That is, are you starting too early or too late or just right? Obviously, we want it to be just right. I'll start by acknowledging my cooperators here, Roger Duncan, Luke Mcelrone, and Bruce Lampinen. Now, is there any reason to worry about starting too early? Well, in walnuts, we found that there is a reason to start worrying about that. And that is that Bruce Lampinen had observed for a number of years that when he saw symptoms like these in walnuts in the midsummer, they were associated with trees that were too wet in the spring and not flooded too wet, just tree too wet as measured by the pressure chamber. So we've been doing an experiment. We had 2 sites. We have 6 years in one and 3 years in another, and found that we could wait a substantial amount of time, more than 1 month after growers normally start irrigating. And we've not seen any bad effects on yields, but we have seen a better tree appearance in the trees. Now, we haven't actually seen any serious symptoms like this, but at least delaying irrigation for long times has had no detrimental effect and some positive effects. So that's starting too early. What about too late? Well, there's the bank account effect. And that is that if you wait too long to start, then trees are going to use up a lot of water in the deep soil, and they're going to run out of that bank account when it comes harvest time, when you have to turn the water off to harvest. Now, there's a lot of reasons to worry about this. In peaches and also in almonds, it's been found that if the trees are too stressed at harvest or after harvest, or even late in the summer, then you can get deformed fruit. And Dave Goldhammer also showed very clearly if they have severe stress post-harvest, that you will have a huge effect on yields of next year. So one question is, why does stress this year affect yields next year? So I'm going to go over this pretty quickly because I think everyone understands what's going on with the bloom and with what's going to be the bloom next year. So if you have bloom this year in February, inside that bloom, there's buds that will be the flowers for next year, and they're still in the process of waking up. In fact, it takes those buds kind of a long time to get to wake up and to decide that they're going to be flowers. So during the spring and the summer, while you're growing your crop, those buds are still producing just leaves or bud scales. And all the way through until mid-July, when your blank nuts are splitting, those buds haven't changed very much. They're still producing leaves and bud scales, even all the way until you start split. But right about that time, late July, those buds start deciding that they're going to be something new next year, and they go through various stages of flower development, which is at a microscopic scale, but you can see it. And all the way through when you're shaking the trees and harvesting the trees, those buds are turning into the flowers for next year. So by the time you get into September, you've got things that are starting to look like flowers. So it's very reasonable to worry about stress during all that time while those buds are developing. But of course, we still don't know exactly how sensitive they are and how much stress it takes to cause those deformities and difficulties. So we'll see if that's a problem when we delay irrigation. Okay, but as I said, in walnuts, we didn't find any more stress at harvest, and in fact, there was a trend that the trees that we delayed irrigation in the early season had less stress at harvest, which was very unexpected, but was pretty consistent. Now, just to put these buds into size perspective here, that bud in September is a very important structure, but compared to what the bud looks like in December, it's really, really, really small. Okay, very small, but very important. So we're gonna be concerned about that. Okay, so what did our results come for this year? So we had two sites, one in Tehama and one in Stanislaus. And the idea is that we irrigated the control trees while they were still at the baseline stem water potential. I'll explain a little bit about that in a minute. But we had two levels of delay. That is, we waited for either 2 bars or 4 bars when they got below the baseline to start irrigating. So the Tehama site was 11-year-old nonpareils. You see the information there about the orchard. The Stanislaus site was a little younger, 5-year-old, and it was on Independence. And they were, of course, on different soils. So what do I mean by baseline stem water potential? Well, of course, we use the pressure chamber. And the idea here is that if you pressure bomb your trees, you refer to this table to find out whether the trees are wet or not, based on whether they're at this what we call baseline value. And that is that these values are what you would expect for a tree that's under field capacity soil. So no soil water limitation of the tree, but still you'll see that if it's cool and humid, you may expect readings in the 5 range. And if it's hot and dry, you may expect readings all the way into the 12 or 13 range, just because even though the soil is wet, the tree is feeling drier and drier when it's getting hotter and drier because it's having to work harder to suck water out of that soil. So they're all negative numbers because the water is under tension and pressure is positive and tension is negative. So, but anyway, the numbers get bigger when it gets hotter and drier. And we know this, what should occur in a fully irrigated tree at field capacity soil. We also have some pretty good ideas in almond about what is a moderate stress versus what is a serious stress. 18 is kind of a moderate stress. We actually recommend that around hull split. If you get into the 30 range, which is not uncommon in production ag at harvest, then you're probably seeing flagging and obvious symptoms of stress, maybe some yellowing and defoliation. But we've taken these trees all the way down to 60 bars, which is well beyond what both of those pictured pressure chambers can measure. So we had to get a special one, but they still didn't die. By the time they get to 60, they're going to lose all their leaves, and you're not going to have any bloom for next year and no crop next year, but they still survive. So almonds are pretty drought resistant. And so what we're waiting for, that is waiting to start until they just get 2 to 4 bars below the baseline, is actually not a whole lot of stress. So we'll see what that did this year. Now this year, on our 2 sites, what we're showing here is the ET value for the orchards. That is how much evapotranspiration an almond orchard under those circumstances would demand. And notice that they both get up to about 40 inches of water use for the season, which is pretty normal for almond. And that in the beginning of this particular season, we had some rains in March and April. And that's why these ET graphs are flat. It's not because the trees were not using ET. We expect that they were using ET, but the rain was just about enough to balance that ET so that their ET demand graph is flat. So that was this year. And what did we do with our irrigations? These are the applied water amounts compared to the ET. And I'll point out a few things. One is that in the Tehama site, there wasn't a whole lot of difference in when we started the controls and when we started the delays. So whereas in the Stanislaus site, the growers were normally irrigating in early March, and so that's when we started. Of course, then after that, we had some rains, but that was about 1 month between when we started the controls and when we started the delay. So a lot longer of a delay in Stanislaus than Tehama in this particular year. Had we not had rain or had more rain, things might have been different. Now, one of the big issues, though, was that you notice is that about the time of harvest in the Tehama site, both the control and the delayed trees were actually ahead of ET because they had put more water on than the trees demanded. So we should have been keeping that bank account real good. Whereas in the Stanislaus site, all the trees were behind ET by the time we got to harvest, which should have been a flag for, there might be a problem here with the bank account. So now let's see what the trees were telling us. Okay, these bottom graph is the stem water potential of the trees, and the dashed line here is the baseline value. So you see we were sometimes close to the baseline, but especially at harvest pretty far away from the baseline, and that makes sense. Now, one interesting difference here is that in Tehama, where we started everything about the same, there wasn't a whole lot of stress in the trees during that period, but as soon as we started irrigating, then that stress difference pretty much went away. So there was not much of a stress, of a holdover for the stress. Whereas in Stanislaus, there was a much bigger effect of the stress on the trees when we were delaying irrigation, and they had kind of a longer hangover. It took them a lot longer to recover and in Stanislaus than it did in Tehama. Okay, but one of the biggest differences between the two sites was what happened at harvest. And this was a real surprise, I guess, to some. That is that at Tehama, where they were technically ahead of the curve in terms of applied water, they had very severe stress at harvest, even getting down below 30, which is pretty stressful. Although there wasn't a lot of symptoms of stress, dropping leaves and that sort of thing. Whereas in Stanislaus, where everything was behind in terms of ET, they actually just were all into mild to moderate stress, or moderate to severe stress, like in the 25s at harvest. So that's what the trees were telling us, regardless of what the ET was telling us. Well, what did the yields tell us? Well, this is just first year, okay, year one. So the trees are telling us that there's no statistical difference in yield or nut quality, nut size, that sort of thing. I'll just point out that, at Tehama, the control was the highest yield, but in Stanislaus, the second delay, the longest delay, was the highest yield, and in both cases, the controls and the longest delay really weren't that different, and there were no differences in nut quality or like shrivel or double or kernel weight. Okay, so the conclusions, as we found previously in walnuts, yes, you get a little bit of stress when you're delaying the trees, but it doesn't end up with a lot of stress at harvest. As we found previously in pretty much every place we've looked, different orchards are different. And presumably it has something to do with the soils, but it may also depend on the tree root health and lots of other things. But the rule is that just because you match ET doesn't mean you're not going to be stressed. And just because you fall behind in ET doesn't mean you're going to have a lot of stress. Now, I know this can be kind of frustrating because for many years you've been taught that ET and stress go hand in hand, but it's clear that soils are very important, and maybe root health and other orchard conditions are very important. So I think it's going to take a little bit more research to try to figure out if we can predict, given a soil and an orchard, what ET is going to result in terms of stress. Once we've reached that threshold, just like we found in walnuts, the other thresholds start falling pretty quickly. So the idea here is that it may not matter too much whether you call the trigger at 2 bars or 4 bars or maybe even more bars, but because as soon as that first one goes, probably other ones are close behind. So it's just a question of kind of letting the trees dry out to some degree before you start irrigating. We don't know about long-term effects. We'll see. And thanks for your attention and for my cooperators. Thank you very much.
Good morning, everyone. Thank you for the invitation to speak in this session. I'm Mcelrone. I'm a research scientist with USDA based in Davis, California. My contact information is listed here at the beginning of the first slide. I will be talking to you today about ET-based irrigation management methods for almonds, specifically talking about older techniques as well as newer techniques that are coming out. With irrigation management, what we're ultimately trying to do is balance the water budget of the orchard. We want to understand the inputs and outputs of this system. One of the major outputs is the evaporation and transpiration from the system, so that the water loss from the soil as well as the vegetation itself, and this is called ET. And then you have irrigation inputs, runoff, and drainage into the system. You can think of this like a potted tree. In a pot on your porch, you pour water into the top of that. Some of it will drain out of the bottom of that pot. Some of it will run off that surface. Ultimately, what we're trying to do is really estimate the exact amount of water that's needed in this system to match the water losses. You can do this in a variety of different ways with soil moisture sensors, plant-based sensors, but what we will be focusing on today is the ET-based component of this. Ultimately, what we want to do with irrigation management is know how much water, when to apply it, and where to irrigate within the orchard. So the tree water use is linked to how much water should be used. Tree water stress is when, so that triggers the timing of these events. And the where is really the spatial variability that you see within these orchards. And we want to time this according to whole split, for example, is one of the stress events that we want to purposefully impose. But ultimately in almonds, we're really trying to avoid stress throughout that season. And knowing these numbers allows us to push those stress thresholds and dial in the amount of water that should be applied. The way that this has been done for a while is with the California Irrigation Management Information System, CIMIS. So this is based on a model that calculates the ET for your crop at a given location. And what it's ultimately looking at is how well would a well-watered model grass use water under those same environmental conditions. So there are these stations throughout the state that look like little weather stations that calculate how much water that well-watered model grass would use. And that gets multiplied by a crop coefficient for this. And the crop coefficient comes from weighing lysimeters, shown on the left-hand side here in the image. And ultimately, what that's measuring is how much would a well-watered almond tree use relative to that well-watered model grass under those same conditions. So this has also been done using shaded areas under the trees. And Bruce Lampinen developed an IPAR app to do this. And you can see in the figure on the bottom left that the percent shaded area actually scales very well with how much ET is coming off. So ultimately, it's how much radiation is being absorbed by that canopy that's driving that water loss through the system. So the methods that I'm going to talk about today for ET actually take it a step further. So what we're ultimately doing with all these newer methods is using an energy balance approach to quantify ET. We want to know how much energy is coming into the system from the sun, and then how much of that energy goes into heating the air, which is the sensible heat flux, how much goes into heating the ground heat flux. And then we calculate the remainder, the latent heat flux is what goes into evaporating water. So ultimately, we're partitioning the energy at the crop surface to try to figure out ET. So looking at this in a more complicated way, the figure on the right shows the two-source energy balance approach. So that's water coming from the soil itself and from the canopy. So we want to account for both of those sources of where the energy is being used going into the system. The figure on the left-hand side of this slide shows how that looks like in a representation of an almond orchard. So you have the almond transpiration, you have the water loss from the soil evaporation, and this can change depending on the type of irrigation. If it's flood irrigation, you're going to have a much greater wetted area of the orchard, or depending on rainfall, you'll have more of that soil evaporation versus drip irrigation, where it's coming from a much more localized situation. I'm going to start off talking about ground-based sensors and then move into an integrated project where we're actually going from towers up to drones and bi-wing planes to satellites that are actually all using these same sorts of approaches. So this figure here actually represents the sensible heat flux. So this is the energy that is exchanged from the canopy to the air. And there's a video here that plays along. And the video actually shows air moving across the crop surface, interacting with that crop surface and exchanging energy. And you can actually see these eddies being pushed out of there. What we must account for with these methods that are the ground-based ones is the direction of the prevailing wind. So that wind comes across the surface, picks up the signature of the water and that energy exchange with the surface and delivers it to a sensor downwind. And you can see that with this windrows example here. The wind would be coming from the northwest towards a sensor located at the center of this windrows. Those of you that have seen me talk before have seen that the way that we originally did this was with surface renewal. Was a method that was developed by UC Davis collaborators. And the idea is that you have air parcels coming in contact with the canopy. They're heating up or turning red, and then the surface gets renewed. So a new air parcel comes in and exchanges with that one that's existing. And this is reflected in a temperature response, where a big drop in temperature that you can see from these ramps. Theoretically, it looks like these ramps. In actuality, this is a data set across the bottom of this. And Tom Chaplin, the founder of Thule Technologies, actually did his PhD work to resolve the math in my lab, to resolve the math here for figuring out the signatures here. Ultimately, he went on to form a company called Thule and developed a commercial system. And they developed a software stack to make this commercially available to growers. So going from a research grade system into this commercially viable. We calibrated this system, images at the left showing surface renewal versus lysimeter with modeled net radiation where it fits very well. We've continued to do this for the almond lysimeter. Now switch the picture there on the left. And you can see that it's a good tight fit of that data, but we're still working on why the slope is offset for this. And we're evaluating the stress conditions for this. And there are other companies like Arable, and the picture in the bottom right shows the Arable mark system that uses these energy balance approaches to get at ET within these systems. We're continuing our work on ground-based sensors with infrared radiometers. These have been used traditionally for looking at water stress of the crops by measuring the canopy temperature. And we were comparing that against the fine wire thermocouples that are used for the surface renewal method. These are pretty wimpy sensors that will break in the field pretty readily. And we wanted more rugged sensors that could give us information about the water use and the stress conditions of the canopy. We started measuring these at 1 hertz frequency, and we actually found that there were ramps similar to the temperature ramps that we had seen from surface renewal in the air in the canopy temperature itself. And when we went through the calculations of this, of doing the math with the new wavelet method, we actually were able to find a very tight relationship between the water loss, the evapotranspiration from this new IRT method, with that of the flux systems that we were using. We're currently developing online tools and instructional videos for this to have this in a citizen scientist model where we work more closely with growers. In the last few slides, I want to tell you about a project that I've been involved in called the GRAPE Remote Sensing and Atmospheric Profiling and Evapotranspiration Experiment. So this is GRAPEX. We are now translating this into almond orchards. And ultimately, the goal of this is to refine and apply multi-scale remote sensing ET tools for managing water use and irrigation. So what we're doing is using these same energy balance approaches and partitioning energy that is captured with Landsat satellite images of the Earth's temperature. And then we are ground truthing those. A lot of sensors on the ground to look at the flux compared to what is coming from the satellite imagery there in the bottom left-hand side of that. We're also, an important component of this work is working with UAV specialists. So they have drones of various types that go over there, quadcopters seen in the middle image, and bi-wing planes that can fly much higher and carry a larger payload. And we have a map here of a vineyard showing the ET maps that come from this. in spatial resolution, as well as the ratio of transpiration to ET, so getting a stress estimate for this. And this work is done by Alfonso Torres with Utah State and Aguirre. And here's an example of an almond orchard where we've done this initially. And you can see a situation where the transpiration is very high. The ET is very high in this case, but the ratio of transpiration to ET is low. So the trees are actually not using that much water. So it could be that there is a lot of soil evaporation in this portion of the orchard. We're also doing this with the 1 Hertz method that I described before, with wavelet method, and taking 1 Hertz images using drones above this. And we feel like it's really pushing forward what the drone capabilities could do for mapping ET in real time. And finally, in this last slide, we are translating this with a new CDFA specialty crop block grant where we partnered with the Almond Board of California to do this. And we're starting a T-REX project looking at tree crop remote sensing of evapotranspiration. And this ultimately feeds into the OpenET project that you'll hear about from Forrest Melton in the next talk. And we really want a ground-based truthing of the model outputs that are coming from the ET for the OpenET system. Thank you.
My name is Forrest Melton, and I'm a research scientist with NASA Ames Research Center and California State University, Monterey Bay. This presentation will provide a preview of OpenET, which is developing an operational system for mapping field-scale evapotranspiration and making that information easily accessible to growers and water managers across the western U.S. When OpenET goes live next year, it will provide data at daily, monthly, and annual time steps at a spatial resolution of 30 meters by 30 meters, or about 1/4 of an acre per pixel across the western U.S. I'll begin with a brief overview of OpenET and conclude with a demo of the OpenET Data Explorer shown here. OpenET is a collaborative effort by many of the leading scientists in the field of remote sensing of evapotranspiration, and includes the developers of many of the widely used models for calculating ET from satellite data. The team includes scientists and software engineers from 3 federal agencies, 6 universities, the Environmental Defense Fund, Google, and the web development firm Habitat 7. OpenET is bringing together many of the widely used approaches for satellite mapping of ET to develop an operational system that provides accurate evapotranspiration data for a wide range of crops and vegetation types. Evapotranspiration, or ET for short, is of course the process by which water evaporates from the land surface and transpires from plants. In the western U.S., ET is the second largest component of the water cycle and can be thought of as the opposite of precipitation. It is the water that leaves the land surface and returns to the atmosphere, and as such, it's a measure of the water that is lost to a local system after being applied to the landscape. Some applied water may also recharge a groundwater basin or return to a canal or a local stream. But in many situations, that water returns to the system and is available for other uses. In contrast, ET is the water that is effectively lost from a basin. As a result, managing water without accurate ET data is like trying to balance your checkbook without knowing how much you are spending every day. ET data is important for a wide range of water resource management applications, including the development of more realistic water budgets, developing incentive-driven conservation programs, providing proper credit to agricultural producers for past investments in conservation to reduce water use, reducing the transaction costs for water trading programs, and support for continued advances in on-farm water use efficiencies through improved access to ET data for irrigation scheduling and management. OpenET has taken a user-driven approach from the beginning, and development of the platform, Data Explorer, and data services have been informed by 12 use cases across the West. Use cases include applications of ET data for groundwater management, irrigation scheduling, and water trading, among others. For irrigation scheduling in particular, we recognize that ET data are most valuable when they are combined with information about the irrigation system, distribution uniformity, soil type and texture, and other information. To support this, we have developed an application programming interface that facilitates automated retrieval and integration of data from OpenET into existing irrigation scheduling software applications, including tools like the Almond Board of California, California Almond Sustainability Program, tools and calculator, and the CropManage irrigation and nutrient management decision support system developed by the University of California Agriculture and Natural Resources Institute. OpenET is driven with publicly available satellite and meteorological data, along with publicly available field boundary information to calculate summaries for millions of agricultural fields across the West. All models are implemented on Google's Earth Engine platform, which provides a shared cloud computing platform for production of ET data using the ensemble of models. Results are stored in a geodatabase and accessible via the Data Explorer and the API that I just mentioned. The API was developed to make it easier to integrate data from OpenET with other applications, including irrigation management and scheduling tools, other farm and ranch management software applications, water data information systems operated by local, state, and federal agencies, and water trading and water accounting platforms. In the past, I think the availability of ET data from different providers and models has at times been a source of confusion and even a barrier to more widespread use of ET data in water resources management. OpenET is a bit unique in that it takes an ensemble approach. The team is bringing together many of the most widely used models in the US, comparing them to understand and explain the similarities and differences, and then taking advantage of the strengths of each model to generate a single number from the ensemble that represents the most accurate estimate possible for each crop or vegetation type, season, and region. OpenET is driven primarily with Landsat data, which provides information at a resolution of 30 meters by 30 meters, or about a quarter of an acre per pixel, but it also incorporates data from other satellites to provide a robust set of inputs to support reliable data production across the western US. Finally, OpenET is currently conducting the largest intercomparison and accuracy assessment to date for satellite-driven ET models. The team is comparing the satellite-based ET data to ET data collected at over 150 flux tower locations across the US. These flux towers are instrumented with scientific-grade open-path eddy covariance instrumentation and infrared gas analyzers, and the instrumentation at each site typically costs around $50,000 per station. In addition to quantifying the accuracy for each individual model through this approach, the team will also use the results from the analysis to identify the best performing models for each crop and vegetation type, and will only use those models to calculate the final ensemble value. For many of the models, this is the first time they've been run on Earth Engine over an area the size of the western US. Because of this, the OpenET team is taking a two-phased approach to the accuracy assessment study. 40% of the flux tower sites are used in phase 1 to allow the teams to identify and fix errors in the automated implementations, and 60% of the sites are being held back for a final blind accuracy assessment and intercomparison. An example from the phase 1 results is shown here for almonds. The scatter plot on the left shows the agreement between the flux tower ET on the x-axis and the satellite-based ET on the y-axis. For 4 of the 5 models shown, we see very good agreement with slopes for the best fit lines between about 0.92 and 0.99, indicating minimum bias error, and with root mean square error values of between about 0.5 millimeter and 1 millimeter per day, and R-squared values almost all above 0.9, showing excellent agreement. The time series chart on the right also shows excellent agreement for most models against the flux tower data, and the results for almonds are highly encouraging overall. And a second site shown here with very similar results, and again slopes for 4 of the 5 models close to 1, indicating minimal bias error, RMSE values in the range of 0.5 millimeter to 1 millimeter per day, and R-square values for the models between about 0.86 and 0.94. I actually expect the results to become even a little bit stronger after the teams complete the final version of their models this month and we conduct phase 2 of the intercomparison. Again, we will be using the results of that final blind accuracy assessment to select only those models that perform well for each crop type and land cover type for inclusion in the final ensemble value from OpenET. And we'll be working with Andrew Mcelrone and his team to conduct additional evaluations for almonds over the coming year. It is important to note that the models are not assimilating any local data from these sites, and they are not being tuned or calibrated to any of the validation sites. What I'd like to do next is to provide a short demo of the OpenET Data Explorer, which will be going live during the first half of next year. The OpenET Data Explorer will provide access to ET data for millions of fields across the West with just a few clicks of a mouse. The system currently has data for about 3 million fields, and the geodatabase stores over 4 billion data points. And once we extend the data record back to 1984, the start of the Landsat data record, the geodatabase will store over 100 billion data points. In addition to the field summaries shown here, data is also available at the original satellite resolution of 30 meters by 30 meters, or about a quarter acre per pixel. That's available across the western U.S. for all vegetation and land cover types. And information is also available for multiple years. You can toggle back and forth between millimeters and inches, turn on the names of cities to help navigate, and the colors correspond to the information shown in the legend on the left. Now, just to show you how it works, I'll zoom in here to the area to the northwest of Bakersfield in the southern San Joaquin. And you can see that once you get into about zoom level 12, simply by placing your cursor over a field, it will display the monthly ET time series, the crop type information, and the acreage. Again, these are publicly available field boundaries obtained from the California Department of Water Resources and originally produced by LandIQ. And then if we go ahead and click on a field, it's going to make a call to the geodatabase, and it's going to actually retrieve the time series for that location from the geodatabase. And this is showing the ensemble average. Each data point is the total monthly ET in inches. That's the depth of water in ET in inches. You can also view the range across the different ensembles and compare data from individual models to the ensemble mean and to the ET values from other models. So you can get a sense of the range across the different estimates. Switching over to the cumulative, we can see that as we saw in the time series, ET was increasing from year to year, likely as we went from the second leaf to the third to the fourth and fifth leaf, seeing the increase from 20 to 38 to 50 inches. You can also compare that to the reference ET information. Reference ET for California is coming from the Spatial CIMMYS data product. See that was consistent. And we can easily compare ET from that field, which we saw was developing as it matured to a more well-established orchard, and see that the ET for nearby orchards was in the range of about 60 to 63 inches per year, about 5 acre-feet. And again, if there's a location that's of interest for which there's not a field boundary available, simply by turning on the raster layer, you can click on any location of interest to retrieve the ET for that data, and information can be downloaded both as graphics, as images of the maps, or as in CSV or Excel compatible formats. And again, OpenET will go live during the first half of next year, and please don't hesitate to reach out to me if you have questions or recommendations for the OpenET team to improve the value and utility of OpenET for almond growers in California. Thank you.
I'm going to be talking about data-driven smart irrigation management in almonds. The first research I want to talk about is understanding water use of young almond orchards. This slide shows a first leaf orchard and a second leaf orchard, and you can see that the canopy size can vary significantly between different ages of orchards. We conducted a study near Corning, California, where we were fortunate to find a grower that had planted 3 different orchards at different times. So we had a first leaf orchard, a second leaf orchard, and a third leaf orchard at the same location. We installed flux towers in each of these orchards in order to determine crop water use, and from crop water use to determine crop coefficients for the different ages of almonds. At each orchard, we had a flux tower that had a net radiometer to estimate the net radiation, a sonic anemometer to estimate the sensible heat flux, and soil packages to estimate the soil heat fluxes. And from this energy balance, we could estimate crop water use or evapotranspiration. And from actual evapotranspiration, we could estimate crop coefficients. This is a graph showing crop water use of a second leaf orchard that was planted in 2018. The spikes here correspond to irrigation events. And if you add a third leaf orchard that was planted in 2017, you can see there's a significant difference in crop water use between these different ages, especially during the middle of the season in June, July time period. And so if we add a fourth leaf orchard that was planted in 2016, we actually see that there's not much difference between the third and the fourth leaf orchard, but the fourth leaf orchard is significantly different from the second leaf orchard. If we add a fifth leaf orchard, again, we see not much difference between the fourth and the fifth. So once these young orchards reach about 4 to 5 years, the differences in crop water use are not significant. On the right here, we show cumulative water use. If you wanted to know how the total amount of water to plan for the different ages, here on the y-axis, I have cumulative water use. On the x-axis, I have days from full bloom. For a third leaf orchard, you'll need about 35 inches. For a fourth and fifth leaf orchard, you would need to plant for about 40 to 43 inches. Theoretically, this is how we estimate crop coefficients as a ratio of the actual crop evapotranspiration over a reference evapotranspiration. And the table here describes all these theoretical variables. But to summarize this information into a form that is usable to a grower, we plotted this graph of crop coefficients on the y-axis and age on the x-axis. When the orchard is just 1 year old, the crop coefficient you need to use is 0.4. And when your orchard reaches 4 to 5 years, on average, you'll need a crop coefficient of about 1. This data could be further generalized using canopy size or light interception. If you have a way to measure light interception, which is the x-axis here, you can use that also to estimate what type of what crop coefficient to use in your irrigation scheduling. Second, I would like to talk about site-specific irrigation management by variety. As you know, most orchards are planted with different varieties to optimize pollination. So our hypothesis was, can we further improve irrigation if we irrigated each variety differently? We conducted a study near Albuquerque, California, in a 5-acre orchard. This study was conducted at the NICO Soil Lab. We designed and developed a program that allowed us to control irrigation to each row. This is Kelly in the orchard and showing the solenoid valves and the flow meters on each of the rows. This was the experimental design. It was a split randomized block design experiment showing the different irrigation strategies. These are the colors here show the different irrigation strategies. And I will explain what each irrigation strategy is on the next slide. For example, in the first irrigation strategy, we deficit irrigated, or when we reached whole split, we cut irrigation to 75% of ET for all varieties when the non-paro, which is the green, reached whole split. So we cut back irrigation and then increased after harvest. And in the second strategy, we deficit irrigated at whole split according to each variety. For example, when non-paro reached whole split, we cut irrigation to 75% while continuing to irrigate Aldrich and Butte at 100%. And when they reached their whole split, we cut back accordingly. And we repeated the same protocol, but instead cutting back to 50% of ET at whole split. These are findings from the 2019 growing season. The key thing here to notice is that these different strategies 1 to 4 were not significantly different in each of these different varieties. where A is Aldrich, B is Butte, and N is Nunpero. There was a significant difference in yield between these different varieties, but that is already known, and really that was not the main focus of our study. When the letters are similar, that means these treatments are not significantly different. We observed similar results in 2020. We see no significant differences in these different irrigation strategies, S1 to S4, for each of these different varieties. However, we saw a significant increase in yield for the Aldrich variety compared to 2019. Third, I'd like to talk about zone irrigation management based on soil type. As you know, soil can have a big impact on spatial variability in terms of canopy growth as well as yield. We worked with a grower near Corning that has over 500 acres of almonds that have been planted on very variable soils. These soils range from heavy, deep clay soils to layered soils where you have a heavy soil on top and light soils at the bottom. And then you also have light soils here in different parts of the orchard. So the goal was to break the orchard down into different zones that have more or less similar infiltration rates and water holding capacities. We see that the stem water potential was not substantially different in these different soil types. This box plot shows stem water potential on the x-axis, and you can see here we have light 1, light 2, heavy and layered soil, and the stem water potential is not substantially different. Again, this is stem water potential throughout the season. Of course, the y-axis here shows bars below baseline, and you can see the stress increasing towards harvest, and then due to post-harvest irrigation, the stress decreases. But again, we were not able to see a significant trend in stem water potential as a function of these different soil types, whether layered soil or light soil in this particular block. Finally, I would like to talk about emerging soil and plant water status sensing technologies for data-driven smart irrigation in almonds that I believe would have a significant role going forward. We've been working on promising irrigation scheduling technologies using cosmic ray technology, which can measure soil moisture over the entire orchard instead of point measurements of soil moisture. And I'll show you our preliminary results. We have also been evaluating automated microtensiometers for measuring stem water potential as a surrogate for the pressure bomb or pressure chamber. These are results comparing a pressure chamber, which are the orange dots, and the microtensiometers, which are the blue curves, in each of the blocks that I showed earlier. And we have these in 12 trees. And as you can see, once these sensors are calibrated, they provide good agreement with the pressure bomb. A pressure bomb, as you can see, Kelly using it here, can be very laborious because you have to go at solar noon, get a leaf, and take a measurement. Automated sensors that can give us acceptable data would be very welcome. Here we again see the goodness of fit for these different sensors, and we're happy to see that the root mean square error was less than 4 bars in all our measurements, and the R squared for most of the trees was about 0.7. We have also been working on remote sensing of both evapotranspiration and soil moisture. And you can see there can be special differences in evapotranspiration even within the same block. For example, here you see that there is less water use in this part of the block, which, as you remember in the slides I showed earlier, this was a light soil. And here where we had heavy soils and layered soils, you see there's slightly more evapotranspiration. So remote sensing allows us to obtain site-specific evapotranspiration for each block. And if we can connect that to our irrigation schedule, I think that would help us to optimize irrigation scheduling. We've been validating these approaches using very robust eddy covariance methods, and we see good agreement as shown in this graph. You see remote sensing is this brown curve from IRRiWatch, and this is a commercially available service that could be either obtained from IRRiWatch or Gen Irrigation. And we also looked at a few other remote sensing models. These are promising results from cosmic ray soil moisture sensing. The blue is a cosmic ray. The brown is from remote sensing, and the dots are from an in situ neutron probe, which you have to take in the field and push into the ground. We see here a good agreement between the cosmic ray and the in situ neutron probe, especially at 75 centimeters early on in the season. And we're still trying to understand the differences that occur during harvest. Finally, we have also been working on high-resolution soil moisture remote sensing from aerial imagery from series. We take series imagery and convert it into soil moisture and combine that with wireless in-orchard soil moisture sensors to understand spatial variability in soil moisture. This could actually not only be helpful for irrigation scheduling, but also to identify irrigation uniformity problems within the orchard. These different colors show volumetric water content, and this is the legend. Again, thank you very much, and I'd like to acknowledge all my collaborators and students, postdocs, and others. Thank you very much.
All right. Well, thank you again to all the speakers for putting their time and effort together for the betterment of our industry. There are hours and hours of work and talent involved in each of these slides, behind each of these slides that you were able to see. So again, thank you, Ken, Andrew, Forrest, and Isaiah for the excellent talks. And remember that as participants, you're welcome to email the speakers directly if you have any follow-up as part of their presentation. Have a good day. Thank you.